All right, we're going to jump into chapter 17. Chapter 17, honestly, is one of the harder things about 17 is understanding the questions and using the vocabulary. And you'll see that here in a second. This is the table of contents. Electrical potential and electrical patents is what we're going to actually go through today, A and B. We'll get to C and D, current resistance and electrical power, in a later video. So let's go right into it. So the point of this first section, distinguish between electrical potential energy and electrical potential. That's a huge one, and it is one that'll trip you up on the homework and on the bookwork, just because electric potential energy is different than electric potential. And you'll see the difference here in a second. We'll have a different equation. Potential difference, fairly easy to work through, and then solving problems is what we do. So electrical potential energy. Now, before I sat there and said, hey, mechanical energy is just the kinetic and potential. Well, then you figured out it's potential energy plus elastic if there's a spring involved, and now we're going to add potential energy electric, that last little bit on the right-hand side. So our equation has gone from mechanical energy is kinetic potential gravity, kinetic potential elastic, and now it's all mechanical energy is kinetic energy plus potential energy due to gravity, potential energy due to an elastic force, and now potential energy due to an electric force. That being said, let's go ahead and get the calculation. It is fairly simple. You should be able to do it fairly quickly. Potential energy due to an electric charge is just the charge of the object and the electric field strength, which we have to get to, and then the displacement from a reference point. And that's all it's saying is the further away, in some cases, it's actually a better situation where it's less potential. The other one is, just as you can take two positives and you stick them together, well, that potential energy can actually cause a big problem because the radius is so small. And again, you've calculated that in 16. We're going to use it a little differently in 17. So have that equation down. If you need to stop the video, as always, go ahead and do so. Get that equation in your notes. We're going to do calculations in class. So now this is just electric potential. Basically, what must be moved against the forces from a given reference point. It's just the potential charge divided by the charge. So in this case, your potential energy right here, what we've just calculated, divided by Q gives you V. It's just another way to use it, a little different. All right, potential difference. And this is just the change in. So basically, if you have a situation, you measure it, say that's my energy due to an electric field, cool. And then you see the second scenario where it's another, you can actually calculate the difference in your potential energy, and then you find your potential difference. And that's the keys. You have to have your potential energy electric in one situation and another to give you your potential difference. And again, good time to sit there and stop the video real quick. Write down that equation to include the word equation. Helps you understand what you're dealing with, and we will go through specifics, which electric charge, what the potential difference is, and if you do the math quickly in your head or write it out, you should be able to see your labels. So now, in the previous sets, you have an actual field where it's field. Imagine some kid standing in a field. That's what I do. Oh, look, I can measure everything else. Now, the potential difference in a uniform field, however, basically gives you, imagine a flat blanket, and you're measuring a reference point to you somewhere standing on that blanket. It's uniform across, so it's not going to matter if you're at the corner or in the middle or at the very far right corner, far left corner. So it gives you a potential difference in a uniform field. Very rare that actually happens, but sometimes it's easier to do that calculation and understand a uniform field than it is anything else. So now, potential difference. This is kind of what we've already been doing. You guys should understand this. You have a charge A at Q. The Q1 and Q2, in this case, for the picture, are positive charged, and you have a radius between them. You can calculate what we've done in 16. You can sit there and figure out the force and energy between the two, whether they're pushing away, pulling towards each other, so forth. Now, what we're looking for is to capitalize on that force pushing them away and try and get energy from it. Or likewise, if they're coming together, we'll try to get energy from that. So that second bullet, an electric potential exists at some point where the electric field, regardless of the charge. So the idea is saying I should be able to calculate the potential energy between those two moving. Now, I know what you're getting at is, hey, how can we calculate that? I'm kidding. You're not saying that, but here it is. To any reference point. You often sit there and say, we're going to start clear out at infinity, and then you can calculate it for the potential difference at a point near the charge. So this is what it is saying. So that you're looking for the potential difference. You still have Coulomb's constant. You'll continue to use that at a 16. The value of the charge at that point, and then distance to the certain point. And again, this is for a near point versus infinity. Superposition principle we'll talk about in a little bit. But that wraps up the two equations that you need to understand for voltage. It's really quick and dirty. We should have a few questions. If you would, read through the book. They give you a little bit more definition of those things. Also, it gives you a little bit more definition of capacitance. And it's always good fun to actually read the book. I know, I'm joking. All right. Basically, any capacitor is used to store electrical energy. These actually have a lot of uses. The one that keeps coming to mind every time I think of a capacitor is Sherlock Holmes running around with that little wand, zapping that big dude in the game. I think it was Game of the Shadows. Anyway, basically, capacitor store electrical energy. In that case, everything you have batteries. It's a capacitor. Not the exact same thing, but a capacitor can store it in an electrical field. It's pretty easy. Basically, capacitance is the ability of that conductor to do so. Now, the SI units is Faraday, F, which is also equal to coulombs per volt. This is where we start looking at voltage for batteries and so forth. So, how to calculate it? I know that was on your mind. You wanted to do some calculations. Sorry, I woke up fairly sarcastic this morning. It happens. Ratio of potential energy, or the charge to potential energy. That's all it is. This is one of those chapters that literally every equation built on another. If you haven't seen the change in V, depends on the potential energy, difference potential energy. So the magnitude of charge on each plate and the potential difference. So should have picture, actually picture's right there. We'll get back to that. So parallel plate capacitor in a vacuum. We'll talk about E naught. Yes, E sub naught. So capacitance in a vacuum, area of one of the plates, distance between the two plates. This is your constant for E naught. It'll be the constant most of the time. Again, you should be able to write it down. And to answer some of your questions, yes, I'll give that to you on a test because I don't even remember that number, not in the slightest. So coulombs per Newton meter. So here's your picture of this whole thing. You have a plate, charge going through an electric wire or electric field. So between any material between the capacitor plates can change. So basically, short version, if you put a piece of metal in between two electric fields, you could actually, in some cases, make it magnetic. In some cases, you can give it a charge. This is how we actually, one of the ways we can conduct electricity. Used to be made a lot, but it's not anymore. It's inefficient. So to reduce the charge in the center field, you have two options. You can spread the plates or change the field strength over here. It's really your only two options. Should make sense on how that works. Capacitor's keyboard, it's one of the places you use it all the time. It's kind of fun. So you have a plate here, plate here. This material, as you smash the keyboard button, actually comes together and it changes the field strength inside it. Computer reads, hey, look, the field has changed. It's also one of the reasons why you can get stuck keyboards fairly quickly. This is actually a better keyboard than most. Most keyboards have that little click sound. That one would not. So just an example. All right. Potential energy stored in a capacitor depends on the charge and the potential difference. So again, electric potential energy is half of the charge on one plate, obviously because we have one, and then the final potential difference. There's another way to do this, and we'll get into that in class, because if you have the charge on one plate and you have the charge on the other, you don't do the multiply by a half. So that's your equation for right now. There's some form of it. Again, it's another equation to calculate potential energy. This is for a capacitor with two parallel plates. So sample problem we're going to actually do in class, so you don't have to worry about that. And I wanted to see that one. Potential energy. We're going to come back and start using joules again, and you'll start seeing this again. So actually, let's just go ahead and do this. There it is. So capacitor connected to a 12-volt battery holds 36 microcoulombs on a charge on each plate. Again, reading is going to become important. So now you have microcoulombs on one plate. You know it's 10 to the negative 6th. They've moved the decimal, so it's 10 to the negative 5th. Voltage is 12. You plug into the equation because they gave you Q over V. And then, hey, take a look. Oh, look, it's 3.0 times 10 to the negative 6 Faradays. They went ahead and moved it to microfarads. That's totally okay. So again, potential electric, you sit there and say 1/2 the charge on one plate, which you all knew from the beginning. The voltage is 12 volts squared. Then you have potential energy in joules. That's the low, quick, fast, dirty version of this chapter. We will do a lot of calculations. The idea behind this chapter is to get through this one, to get through voltage, and then finally, hopefully, get through capacitors and circuits. We'll see how we do. I know we've got a project coming up, and honestly, quite a few seniors are trying to run out the door. So I don't blame you. All right. Have a good day. I'll see you in class. Don't forget to do the quiz.